So now we'll start with the analysis of minimal residual disease. And in TMH, we have standardized high sensitivity, which is equivalent to that of next generation flow, because we acquire somewhere between 6 to 9 million cells for every MRD sample in multiple myeloma, and using two tubes, and for limit of detection, as I mentioned in my earlier talk, is 20 events, and limit of quantitation we have kept 40 events. So we use these parameters for our reporting. So as we have done in earlier cases, now in multiple myeloma MRD, we have little different approach, because we acquire millions of cells. We especially in cytoplasmic tube, like in kappa and lambda, we see a lot of artifacts and debris which can give non-specific as well as junk which can interfere with the analysis. So here we have adapted a different strategy. Now, what is that different strategy? I will explain you in a minute. So what we do is, first of all, we start with first we evaluate plasma cells. Like we have seen in diagnostic, we go with 38, 138, and 45. Identify plasma cells, clean them a little bit, and then look for antigen expression. Here we started in, especially in cytoplasmic tube, we have adopted a reverse gating strategy. And what is that? So we start with the first kappa and lambda. So as you know, all plasma cells, unless it is a non-producing myeloma, that is the myeloma which cannot secrete or which cannot produce light chain only, so which will be kappa and lambda negative, which is very, very rare. Other than those cases, we use kappa and lambda for the starting gating, because all plasma cell, either polyclonal or clonal, must express either kappa or lambda or both. So we start with kappa and lambda gating. So all kappa and lambda positive cells will be B cells or plasma cells. And after that, then we use 38, 138, and 45 for further cleaning of these plasma cells. And then come to a final plasma cell gating approach. Okay. Now for the character, and then you characterize the plasma cells, identify whether they are abnormal or by antigen expression, or they are clonal. Then we in MRD, as we have mentioned earlier also, so we have to look for the other parameters of hemodilution or the bone marrow representation. So for that, what we do, we look for the mast cells or precursor B cells, that is hematogones. 117 precursor cells, 117, 117 positive, predominantly include myeloid, myeloblasts, as well as promyelocyte, and early precursor erythroid cells. So which, that is 117 positive erythroid precursor cells. Then so these are the three parameters which can usually use for the representation of bone marrow. We can also use normal plasma cells if we have enough normal plasma cell, which can also indicate because of representation of bone marrow. So these are the four parameters which can indicate if the marrow is dilute or not. And it is very important, because if the marrow is hemodilute and if your MRD is negative, then your sample may not be representative, and you may end up giving false negative. So to avoid false negativity, if you see using these parameters that marrow is hemodilute, then we generally give a comment saying that the marrow is hemodilute, and and low level of MRD cannot be detected. But if you see the abnormal plasma cells and MRD is positive, then you can mention the MRD, but you still give that comment if the hemodilution is there, because your MRD level may not be representative. So this is the introduction. So I'll start with the analysis, live analysis, how we do it. So you see, because I have mentioned, now we are using this chain color, but we have acquired a sample on the DXFlex, which has 13 parameters. So we have 3 channels, empty channels. So we use these 3 empty channels to identify non-specific doublets or junk, because these all doublets and abnormal junk gives autofluorescence in these empty channels, and there is no marker, so we safely exclude this population. And if you see that the number of events which we have acquired after excluding the junk is almost 5.4 million or 5.5 million in this tube, and the other tube is equivalent. So we have acquired almost 10 million cells in this sample. Okay. Now, as I mentioned, we start with kappa and lambda. So we take this say all cells. We have not excluded any cell here by using singlet or viability gate. Okay. So we use this we go with F gate, which is junct-free gate. So we take this F gate, and we have now the cells which are falling in kappa, lambda, and the cells which are falling in the center. Now, for utilizing this gate, you have to have good quality of kappa and lambda standardization. If your kappa and lambda right chain standardization is not enough, then you cannot use this kappa and lambda gate, because otherwise, in those cases, you may miss the plasma cells. But we have cross-check with this our analysis and our standardization, and we know that our kappa and lambda is working fine. So that's why we are using this gating strategy, where we use all gating all kappa and lambda positive cells here, and we exclude in this the central cells which are not kappa, either negative for kappa or as well as lambda. So these are not, neither these are plasma cells, neither these are B cells. So this is kappa lambda gate. So what we do then, we evaluate kappa lambda gate further to exclude B cells, and we put kappa lambda gate here. Okay. And then we see even in the kappa lambda gate we have a lot of cells which doesn't look like plasma cells. So these 38 bright positive cells are plasma cells, and the rest of the cells are non-plasma cells, possibly B cells, and there is also some junk because these gates are wider. And you have to keep these gates wide because you don't want to exclude any plasma cells, you don't want to miss any plasma cells which is very close here. So, but in this gate we have excluded majority of granulocytes and T cells which will not side say either kappa or lambda. So the next gate is to identify, to take 38 and 45, check there. Also you can check the same with 38 and 138. It should be 138, okay. So you can see the 38 and 138. We can look at those cells also here based on using 38 and 138. Now, how do you know whether they 30? As we have done in our earlier analysis, we'll give the color to these gates, so to see whether we are where these cells are falling. So we see these cells which we have gated with 38 and 45. They are, you can see they are kappa lambda positive, and then they are also majority of the 138 positive. There are few cells which looks like 138 negative, but they are 38 bright, so we still include them. Okay, and then finally we can combine this. So you see we will give color to this gate also to see if we are missing. So if you look carefully here, the cells which are present in 38 138, there are cells which are here outside this gate. So we know that we have to expand this gate to include them. This is a strategy how to include maximum cells. Now we have included all cells which are present in this gate, but then at the same time we have included some additional cells which we don't want, which may not be the plasma cells. Now so to exclude that, this is our parent gate and this is our next gate. So finally what we'll do is to take this gate and then adjust our cells using 38 and 138 as we have been in our earlier analysis. So we'll take this UG, that is basically means ungated 3845, because we have not done using any singlet or viability gate here. So this is our these are the cells, and we have CD 138 and 38. So if you look at CD 138 and 38, these cells doesn't look like plasma cells. Okay, so we can exclude and we can put a next gate which will be a combination of both 38, 45 and 138, because we have taken the help of all these three markers. So we'll use this. We can label it as a 38 versus 138 and versus 45. Okay, and then because we have not excluded any doublets or non-viable cells, so these here, instead of starting from with the singlet and a viability gate, we have started the otherwise. We have started with kappa and lambda so that we can exclude majority of debris upfront only. But if anybody want to start with this is also right approach, which I have shown in earlier two cases. So here we have 38 138, and you can see the majority of the cells look singlets, and Here we are not excluding doublets here because there are some claims or some belief. There are some people who believe that possibly doublets may represent hyperdiploid plasma cells, and we don't want to miss them. So that's why in plasma cell particularly we are not excluding doublets with larger size and larger area, but we can exclude here the cells which are smaller and still showing lesser height. So those cells can be excluded. So these singlet gates are little bit modified to accommodate possibly a hyperdiploid plasma cells in this. And then we use this PC singlet gate. Now we have labeled it PC singlet gate, and we use this PC singlet gate to exclude if we have non-viable cells. Where is the PC singlet gate? Okay, here. And you can see we have some cells which looks degenerating, some cells viable. So we can exclude these cells which looks like they are reducing in size. They are small in size and side scattered. So possibly these are just dying cells which are there. So we'll exclude these so that we have proper viable plasma cells in our gate. So this is our plasma viability gate, and one more time we can check our plasma viability gate if they are falling, showing the kappa lambda properly, or if there is cells which are coming from the negative regions or a very borderline region of kappa and lambda. You see viable gate, okay. When I said I'm talking about these cells, so these cells which are actually coming from the border, so may not be these plasma cells, and because this gate were broader, they are coming. We don't want these cells, so we exclude these cells, the borderline cells from our analysis. So this is our clean plasma cells. We excluded these few cells which are possibly not plasma cells, and we exclude apoptotic cells. We exclude some doublet. This is our gating strategy. So these are our plasma cells. Okay. So here we have got clean plasma cells which are labeled as clean plasma cells, and then we can use evaluate these plasma cells further. Okay. So I'm starting with the kappa now. We have kappa lambda. It looks pretty polyclonal. Majority of the plasma cells is polyclonal only. Okay. So let's start with these clean plasma cells, and okay, and this clean plasma cells we can give the gates to kappa and lambda separately so that we can identify if there is a mixture of kappa lambda, or only if there are clonal population I only expressing kappa and lambda, there will not be mixture of two colors. So I'm going to switch off this color so that we can get this. I have to switch off two more colors. Okay, let's give this color to this kappa one color and lambda other color, and switch off the parent color. Let's switch off because we don't need it anymore, or we can move this kappa and lambda up. Now you can see here these degenerating plasma cells were actually falling here, and they were also showing down regulation of 38 and 138 in a diagonal fashion, indicating those are actually apoptotic plasma cells which we have excluded from our analysis. And now we have labeled kappa and lambda, so that because we are using two colors, so whenever we are looking at different antigen expression, if they are showing the mixture of these two colors indicating polyclonal plasma cells, and if they show only single color, then possibly those are clonal. How? So let's evaluate them further. Okay, so we can start with 19 and 45. Let's label. Let's get a Residual plot, copy and paste. We can start with 1945. That's how we usually start, and then 1956. So 19 and 45. If you look at 1930, you can see that there are some orange, more orange here. It indicates possibly in this region there are more lambda positive cells, and they are mixture of, otherwise they are mixture of cells. So we have to somewhere some few cells which looks like lambda prominent or predominant in 19 negative, but there are few other cells also. So we need little more cautious gating to identify the correct clonal population. So we'll start with 19 and 45, and let's look at that. So here, if you look at carefully, you see there are few cells which are 19 or 45 negative, and they are orange. So it looks like there is in this region the lambda positive cells are predominant, which indicates that possibly in this region we have more clonal plasma cells as compared to the rest of, because the rest of the cells shows mixture of both orange and blue color, which indicate both kappa and lambda, indicating these are polyclonal plasma cells. And otherwise also, if you look at antigen expression, 19 positive and 45 positive indicates normal plasma cells, but the plasma cells which are 19 45 negative, those indicates abnormal plasma cells. Let's look before gating. We can also look at other markers like 19 and 45. Sorry, 19 and 56. So let's see 19 and 56. Now, if you look at these cells, which are 19, they are also looks like 56 predominantly positive. So these two plots only indicating that we have some lambda restricted plasma cells which are 19 negative, 45 negative, and 56 positive, indicating that possibly this is our minimal residual disease. But we have to purify to get the more than 90% of lambda restricted plasma cell for the MRD quantities. Now we have additional markers also, like we have 27, 81. So let's start with 81. Let's see, we have 81 here. Here again in the 81 negative region, we have more lambda positive cells, and same way we can look at 27 also. 27 negative population, it does not show there is a mixture. In fact, if you look at 19 negative, they are predominantly 27 positive. As I mentioned, not always all markers are helpful, so that's why we have a combination of these markers. Now, because this region is our most suspicious and abnormal plasma cells fall, more than 95% cases, we start from here when 19 negative and 45 negative. Let's put a gate here. Little broader gate. Here we started, which we can label. In fact, if you see carefully, some of the cells are coming on from this border. So some of the cells may not be the true plasma cells. So we have to probably readjust this gate to exclude these cells which are coming from this border. We can do that later, but let's find out whether first. So these are the 19 negative, 45 negative cells, and we can label them 19 negative, 45 negative plasma cells. 19 negative, 45 negative disease. Okay, and then we can try with other markers. Now let's try 19 negative, 45 negative, and we have 56 positive, predominantly plasma cells, which appears all lambda because they are coming from lambda. Then we can look at other two plots. 1945. See here and here again 1945. So they looks like predominantly are 81 negative, most of the cells. They're 27, but it is positive. So 27 may not be the abnormal in this population. Okay. So now the next abnormality is 56 positivity. So we can always gate this 56 positive population. Go to the gate. We have this 56 positive population, and we can look for the light chain restriction. Just readjusting because some of the cells has gone out of our gate. Initial gate is this is jump. It's coming from the gate. we readjust again to exclude these borderline cells, because these borderline cells may not be the true plasma cells. Okay, after exclusion, still we have few cells here, which are 81 negative, 19 negative, 56 positive. If we adjust few more things. So we are adjusted and they are falling into the lambda positive expression. We can gauge them differently using so. So these are the cells which are 56 positive. These are all 45 negative, 19 negative, 56 positive. The lambda restricted 81 also dim to negative and 27 is moderately positive, and their 138 is nicely positive. You can see they are nicely 138 positive indicate. And in fact, if you look at initially they are 38 slightly dimmer. So I mentioned in 30% of cases you can have 38 down regulation in the abnormal plasma cell. So these, if you look carefully here, there is a small population which is including this population. So there are multiple markers, multiple abnormalities, and multiple markers which can confirm that these are the abnormal plasma cells, and rest of the plasma cells are all polyclonal because they are also in the mixture. We can always put different gates on different markers and check whether they are clonality, and this is why the kappa lambda light chain restriction is very important, because it can help you to confirm a small level of disease when you have a lot of normal plasma cells, and other markers help you to pull out the abnormal plasma cells in the background of a lot of normal plasma. So you also see there are some empty gates. What are these empty gates? These empty gates are to identify the other parameters or other population which represents hemodilution or which represent bone marrow representation. So that is what we want to look at is the mast cell and hematogone. So for that we have what we have done. We have looked into the we want singlet cells, but what we have done, we have excluded plasma cells from the. We taken the singlet non-plasma cells so that we can exclude doublets, but at the same time we are not excluding plasma cells because we are using plasma cell in a different gating strategy which we have evaluated. So we have a Boolean gate which says non-plasma cells, and we have all the doublets. So we can exclude these doublets easily, and at the same time we are evaluated plasma cells separately, and these are all non-plasma cell doublets because we want to look at what are the differences, and because these plasma cells are very few in number, does not affect the count of mast cells or anything, or hematogones if we exclude them. So we have this this singlet non-plasma cell singlet gate. You go to non-plasma singlet gate, you have viability gate, and with this viability gate we can look for the other cells. Anyway, other gates like this, or we can start here to find out the other cells. We have already different plots here, so we have gated all singlet gates. We have excluded non-viable cells, and we have included 45 versus hematogones. So this is 45 lymphocyte as well as hematogones gate. You can see we included all cells which are 45 dim and 45 bright lymphocytes, and hematogones generally are 45 dim and low inside scatter, they'll fall in here. Then we apply this gate to the 19 positive cells. So we have these all 19 positive cells here, and these 19 positive cells which include plasma cells, hematogones, everything, and this 19 positive cell gate, you see there are some plasma cells there, and then we identify hematogones by using 20 negative and CD38 positive cells, because hematogones shows variable 20 and moderate level of 38. So these are the cells, and these are mature B cells. So we have mature B cells, we have hematogones here, and because we can still have some plasma cells here, we use 38 and 81, 138 and 81. So the cells which are 138 negative and 81 positive, bright positive, are basically hematogones, and these are B cells. So you can see B cells are polyclonal. Let's give color to that. Here you can see the B cells are polyclonal, and these are hematogones. We can color them too. These are hematogones, and we exclude kappa and light chain expressing cells from them, and these are all kappa lambda negative, 81 bright positive, 38 moderate positive, 20 negative, 19 positive, 45 dim hematogones. And these are 76,000 hematogones in 5 million cells, which if we calculate that, 76,000 divided by 5.4 million cells basically. So that would be 1.4% of hematogones, and hematogones more than 0.05% indicates representative bone marrow. So your hematogones are 1.4, which means the marrow is quite representative. There is no hemodilution. So in this tube there is no 117, so we cannot look at mast cells, and 117 to mature cells. And these are the cells. So let's see how many events were there. So if you look at, we can label it as a minimal residual disease because they all are restricted and shows abnormal antigen expression. I have some empty plots just to look at the different aspect of different combination of these cells. But here we got easily 56 positive, 19 negative plasma cells. We need not to use, where there was no need to use these plots for the different other combination. Okay. So if you look at this, how many cells are there? Take a number, and there are 64. So 64 cells in, we have evaluated 64 cells in 5.4 million cells. So if you look at 64 divided by 5.4 million cells would be 0.001% MRD or 0.0012% MRD. So that is the level of MRD which we get. And because these are 65 events, and our limit of lower limit of quantitation is 40 or more than 40, it is crossing or lower limit of quantitation as well as lower limit of detection. And it is also reaching the sensitivity of sensitivity, high sensitivity, which is indicated by IMWG, that is International Myeloma Working Group, of 1 in 10 raised to power minus 5. Okay, coming to the next tube. Now next tube, because we do not have kappa and lambda, so we are not starting with kappa and lambda, and we exclude, again we use empty channel to exclude non-specific cells or binding cells or cells which use autofluorescence. We excluded them. Then we start, now here and then we start with 38 and 45 again, label them and check with 138 to 38, and we have additional marker, that is 319, which is new marker, because you see the 138 cannot pull all plasma cells. So there are some plasma cells of 138 dim to negative, although because of 38 bright expression we can easily see them. So if you look at here, these plasma cells are there, this one, so we can color them and see if our first gate is including all cells or not. So this is, if you look at this gate, we have given green color to these cells, and you can see these both gates are including all these cells. So these gates are enough. Let's give a color to this color, this 38 and 138, and see if we are excluding. Yes, so there are few cells are excluded, so probably we need to expand this gate so that we can include all the cells. Okay, but these all cells are included with 38 and 319. Let's check whether 38 and 319 is including all gates or not, all cells or not. Okay, there are few cells which are not included in this, so you can see these are, those are these. So they are 38 pretty dim, and the 45 also negative, and they include a lot of junk. So possibly we need not to include those cells. And they are also 319 also dim, and 38 is dim. So we can restrict our gate here. So because this is the parent gate which include all 38, 138 gate, we can make this as a primary gate and apply it on the next gate, the next plot, that was UG38PC. You can see here. So we have few cells here which we can include, and but it looks like these are not, these are the cells which are possibly not plasma cells. How do you confirm? So you take this gate 38, 138, and then we can exclude by using 319. Or if you do not have 319, then you can just, based on the 38 expression and 38 expression, we can still, with fair amount of confidence, we can exclude them with little experience. So we can, for that we need little experience to confidently exclude it that way. So if you look at 31 versus 38, looks best. We include this looks like base gating strategy, and we have applied all 38, 138, 45, and 319. So these are 4 gating strategy. Now these cells are further again excluded using modified PC. Okay, this is modified PC gate, and then we can exclude if there are any doublets, but we fortunately there are no doublets here. And then we exclude apoptotic or dying plasma cells from this gate by using viability gate. Once we have viability gate, we can check for if there are any doublets which are still coming here, which will be 45 bright or non-specific cells. Again, so if there are, now in this there are no such cells, so we can confidently exclude those possibility of having these cells. And then we have these all clean plasma cells, which will further evaluate for them. Now here no kappa lambda, but we know those cells were 1945 dim to negative, those were 56 positive, and those were 81 negative, right? So we can start, or we can start here by using 19 versus 45. Now 19 dim, 45 dim and 19 negative population. We can and then we look at 56. So if you look at 19 versus 56, so there are some cells which are 19 negative and 56 positive, and earlier we have shown that all plasma cells are 56 positive. So here we can confirm these. cells, and we can give these cells a color, different color. Let's get blue color. And of them, all these cells, there are some cells which are 81 positive and some cells are 81 negative. And if you check in first tube, these cells which were 1945 positive, all were actually clonal. So, and there are some of them are 81 positive, some of them are 81 negative. So, we can include all these cells as a abnormal clonal plasma cell basically. So, this is our residual disease, MRD. And in this tube there are only 23 cells. The earlier tube there. So this type of differences we usually note when we look at cytoplasmic versus surface tube processing, because of in cytoplasmic processing we lose some cells. Okay, we can lose some normal plasma cells, or we can lose some abnormal plasma cells or some granulocytes, which can because of that there is some variation can be noted. You can see there are some of them are 81 positive, some of them are 81 negative, 56 positive, and you can see there possibly there are 28 dim positive. You can see as compared to the normal plasma cell, looks like there are 20 and 28 dim positive also. So if you look at 28, there are 28 also positive. So all 23 events are 28 positive, which is another abnormal antigen expression. 56 positive, 19 negative, and 45 negative, 38 negative, 38 dim. So here finally we confirm, we put a gate of MRD. So here we have 23 events in how many cells we acquired. We actually acquired 5.9 million cells in this case. So, or if you take viable cells, we acquired 5.2 million cells. So if you see, we have 23 events in this tube and 64 events in this tube. So if we add them, 64 plus 23, it would be 87 in almost 10.6 million cells. So we can calculate 87 events divided by 10.6 million here, right? 10.6 million. Okay, so it will be 0.00008. So that would be 0.0008, which means 0.8 into 10 to the power minus 10 to the power minus 3, or 8 cells in 10 million cells, 1 million cells. So 8 cells in 1 million cells, because there are 80 cells in 10 million cells. So that is the sensitivity we can achieve, and this is as good as next generation flow. Only in next generation flow we use automated analysis, where you can use the PCA or PCA if you have fixed markers, and if you have the expression pattern of all these markers, and compare with the data bank which is there with Euroflow, and this data bank include basically all markers expressed in normal plasma cells, and using the mean fluorescence intensity or geometric means of this marker, you can apply PCA, that is principal component analysis, which differentiate normal and abnormal plasma cells using the software Infinicide. It can be used. Now that is MRD, but we also want to look at other parameters. So for other parameters, we have hematogones. Okay, next. For other parameters, we want to look at, one is hematogones. So hematogones we have seen in earlier tube. So in this tube, we will look at mast cells. You can see the 117 bright positive, 45 moderate positive. Mast cells are 0.01%, which indicates this is also representative, because mast cell above 0.002% and above are basically considered as a representative marrow as per the Euroflow. Then we can also look at hematogones also here, because these are the plasma cells, but we have 38 bright and 19 positive cells are basically hematogones, in which with the help of 81 and 38 we can confirm these are hematocones. So for 117 we have 117 precursors also, so we can adjust the gate with 117 here. You see 117 positive 45 deemed positive population basically include blast, that is myeloid blast, we have promyelocytes as well as some pronormal blast, so which indicates it. So if you have more than 1.5% of these, that is also sufficient, sufficient to say that this marrow is representative. So we use multiple parameters, but mast cell and hematocones are more reliable. Third, if those parameters cannot be counted, then we can look at the 117 positive. So generally in our reporting we mention all these parameters because we're still monitoring which is the best parameter to identify, or to rely on best parameter to rely on for hemodilution or representative of bone marrow. Now, if you are using unstained cells, we also acquire unstained cells to see the autophagy of the cells. And these unstained cells not only give autophagy, but we add CD45 and 10 to see how many neutrophils are there, CD10 positive granulocytes are there. So if you have CD10 positive granulocytes which indicate neutrophils, usually in bone marrow, representative bone marrow, they are less than 30 to 40%. More than 60% may indicate hemodilution. In AML MRD, more than 90% is considered hemodilution. So we are also monitoring 10 positive granulocytes to look at hemodilution. We don't know which cutoff is best, but if we have more than 60%, definitely there is some hemodilution. So this was about the MRD analysis and other quality check. So we use both the tubes. You see the kappa and lambda light chain restriction is very important to identify cells. And in the absence of which, unless you have very good experience and your all setup is very well standardized, you can it can give you trouble to confirm the diagnosis. So personally, we believe that kappa lambda is very important for the MRD analysis. I think I will stop here. Thank you.